Hi everyone, welcome back to my channel Chiru's Aspirations. And from today, my channel name is going to be Mathematics Appetite. So once again, welcome back to my channel, that is Mathematics Appetite. I'm back with many amazing and phenomenal mathematical concepts. So we are going to have the major and very fantastic, beautiful journey of mathematics. So I'm going to come up with the engineering mathematics, that is M1, M2, M3 and M4. So we'll be enjoying the mathematics and we'll get into that zone, that core of mathematical concepts and enjoy it. And also I'm going to come up with BSc mathematics also. So all the 6 semesters mathematics I'll be coming up with that, and also an intensive course of the coordinate geometry I'll be doing that. So because coordinate geometry is very important, very interesting also. A separate session series of videos will be coming up of coordinate geometry, and also I'll be doing the 10th standard CBSE board. I've already done many chapters and I'll be continuing it. And today the topic what I'm going to do is, that is the engineering mathematics first sem successive differentiation. It is differential calculus. We'll be seeing what is successive differentiation and the standard forms of successive differentiations. So now we are getting into it. And by the way, the people who are new to my channel, I am Chiranjeevi. This is Mathematics Appetite. Okay, coming to the successive differentiation, what amazing concept it is, because calculus itself is a beautiful mathematical concept. Without calculus, nothing is possible in the world. Every calculations, every observations, every pattern we do in the nature, we need calculus to calculate it. Anyway, we are going to see, you have studied the calculus in your POC, that is the limits, derivatives, differential equations, all those things. So today we are going to discuss about the successive differentiation. Which means so we are going to discuss the successive differentiation. Okay, we are going to see, because derivative of a function you have seen in your POC, right? What is the derivative of a function? If we have a function y is equal to f of x. First of all, what is a function? I hope you know it. So a function, so where we'll be having the independent variable x and the dependent variable y. If we plot this, the x quantity will be varying as the y will be varying. Y is dependent on x. So the instantaneous change, whatever the change happening, the instantaneous change if we calculate, that is nothing but derivative, right? Like example, the derivative of x to the power of n is nx to the power of n minus 1. For sin x it is cos x, like this. Okay, so a derivative is nothing but the instantaneous change, what is happening there at that particular infinitesimal very small place, right? So that we call it as derivative. So this is the differentiation what we do. Any function if we take, we differentiate it like this, isn't it? Yes. Okay, let us see what is successive differentiation. Any function if they give, for example, let me take a function that is y is equal to x square plus 3x plus 5 plus 4, something like this. If we want to differentiate this function, how we are going to differentiate? We know dy by dx is nothing but dy by dx of the function that is x square plus 3x plus 5 plus 4. That is nothing but, so we are going to differentiate what is the derivative of x to the power of n. D by dx of x to the power of n is nothing but nx to the power of n minus 1, isn't it? So I'm going to apply here, so we'll be getting 2x to the power of 2 minus 1, that is going to become 1. I hope you are understanding. Plus 3 is a constant and x is 1, obviously we'll be getting this as 3, because whenever there is 2 variables or 2 quantities like this, so we are going to use product rule. First into differentiation of second will be 3 plus second into differentiation of first, differentiation of a constant term is 0. So we'll be getting 3, the derivative of 3x is 3 plus 5 is constant, 0 because derivative of a constant term is 0, right? Plus 0. So you will be getting 2x plus 3. This we have studied already in the PUC, how to differentiate a function, isn't it? So we are going to see what is the successive differentiation. The word itself, it indicates that successive means the repeated, which means we are going to repeatedly differentiate that particular function. For example, here we have considered an algebraic function, right? X square plus 3x plus 5 plus 4. I have differentiated, I got 2x plus 3. I am going to differentiate it again. I got dy by dx as this one. I am going to differentiate this again. So what I am going to get? D by dx of dy by dx is equal to, what is the derivative of 2x? It is 2, right? Plus, for 3 it is 0. So d into dy, that becomes d square y by dx square, that is nothing but 2. Okay, so there is a given function, we are differentiating it, we got 2x plus 3. Again differentiating this, we got 2. This is the second derivative. Okay, the first derivative is dy by dx, or it is also indicated in the form of y dash or y1. Okay, the first derivative dy by dx can also be represented as y dash or y1. Also, dy by dx of dy by dx, that is the second derivative, can be written as d square y by dx square, or we can write this as y double dash or y2. Any one representation you can give for the second derivative. Okay, what about the third derivative? It's simple. Again differentiate this. What happens? We have d by dx of d square y by dx square. What happens if we differentiate again? It is a constant, so it is going to become 0. Further, we cannot differentiate it, right? So this is nothing but the d cube y by dx cube is nothing but 0, or you can represent this as y triple dash or y3. These are the representations, and this is called as the successive differentiation. So a given function, we are going to differentiate with respect to x, here yx. So after differentiating it, so here we will be getting the second derivative, that we can represent it as y dash or y1 or dy by dx. Again, after this, if we differentiate again, whatever the function after differentiation, whatever the answer we have got, again if we differentiate the first derivative, we will be getting the second derivative. Again, if you differentiate the second derivative, you will be getting third derivative. Again, if you differentiate the third derivative, you will be getting fourth derivative, fifth, sixth, seventh, and it goes on like up to the nth derivative. Soon we will be seeing the nth derivative of the functions. Now the question arises. We know that if we differentiate a function, what is going to happen? Why we need calculus? Why we need to differentiate a function? We need to know the instantaneous rate of change, what's happening at that particular instant, whatever may be the function. It may be the trigonometric functions, the algebraic functions, logarithmic functions, etc. So any function, if we differentiate, what's going to happen? That instantaneous rate of change will be getting, isn't it? So once when you differentiate again, if you go for second derivative or the third derivative, what's going to happen is, so we are going to see how the curve varies. That is, we are going to study about the concavity and the points related to the graph. So it is very early to understand all those things, but in general there is a necessary for successive differentiation in getting how the curve is varying, what is happening to the curve, how many concave up, concave down. So all these points, if you want to analyze the complete structure and behavior of a curve, how it is happening, of a function of course, then we need this successive differentiation. I hope you people are understanding. Yes, so this is the concept of the successive differentiation. Let me take some other example and show how we are going to solve the successive differentiation. So I have taken some algebraic function. Let me take some trigonometric functions. So if I take y is equal to sin x, let me take some simple function. So y dash or y1 or dy by dx, any one thing you can represent, that is nothing but, how will you differentiate sin x? You know, it's just a formula, right? The derivative of sin x is cos x. It's as simple as. Okay. Now I'm going to go for the second derivative. Directly I'm going to write. You can write anything like y2 or d square y by dx square. That is the thing. But what is the derivative of cos x? It is minus sin x. Okay. I'm going to the third derivative. That is the thing. But minus, what is the derivative of sin x? It is cos x. Again, fourth derivative. Again I am differentiating it. So minus, for cos x it is minus sin x. So it's going to become plus sin x. So it goes on like this. Okay, the first derivative, second derivative, third derivative, fourth derivative, and so on. So this concept is called as the successive differentiation. I hope you are understanding. Yes, how interesting is this? Yes. So now we'll soon go to the generalized form of nth derivative. Okay, I found the first derivative, second derivative, third derivative, fourth derivative. If I want to find the 50th derivative, if at all the function exists till that, when we take n is equal to 50, till that if it exists, then I need to find it. So is it possible to do 50 times the differentiation? No, it's not possible, right? So we have a generalized formula for some standard functions. From standard form of functions, we have generalized nth derivative. We'll be seeing that, and I hope you are enjoying it. Yes, we'll see that. So the first standard thing we have is, so here okay, the first standard thing we are going to take is as y is equal to e to the power of ax. This is the first standard thing. Let us find the nth derivative of this function y is equal to e to the power of ax. What is going to happen? So y is equal to e to the power of ax. Let me take the first derivative, y1, that is nothing but, what is the derivative of e to the power of x? It is a into e to the power of ax. Isn't it? This is the derivative of e to the power of ax, right? Yes, this is the first derivative. Let me take the second derivative. y2 is equal to, already I have a constant term, I will be putting here, and again differentiating this, what we are going to happen? So here again we will be getting a into e to the power of ax. Isn't it? Okay, so what happened here? It is a square into e to the power of ax. Again I will go for the third derivative, that is the third time the successive differentiation happening. So a square is the constant. Again I am going to differentiate this e to the power of ax. So again I will be getting a e to the power of ax. Okay, so that is nothing but a cube into e to the power of ax. It goes on like this. If you observe, there is some pattern with respect to this. So if you observe y1, the first derivative, we have a into e to the power of ax. If you observe the second derivative, we have a square into e to the power of ax. If you observe y3, it is a cube into e to the power of x. What is the pattern? The pattern is, here the a power is increasing, right? Here it is a to the power of 1, a to the power of 2, a to the power of 3, and e to the power of ax remains constant. It remains the same. If you take y4 also, you will be getting a to the power of 4 into e to the power of ax. Then, how can we generalize this? Yes, we can generalize this as yn is nothing but a to the power of n into e to the power of ax. So this is the nth derivative of the function of the form y is equal to e to the power of ax. We have generalized this function. Okay, yn is equal to a to the power of n into e to the power of ax. So yn can take any value, like, let me take the 10th derivative. The 10th derivative of this function, if you 10 times differentiate, what's going to happen? You will be getting general form. We have general form, we have derived the general form, right? So you will be putting a to the power of 10 into e to the power of ax. Because for each differentiation in this function, if you observe, for successive differentiation, one a is increasing here. As a result, the power of a increase. So obviously for y10, okay, you will be writing a to the power of 10 into e to the power of ax. For y3, 8 cube. For y10, it is a to the power of 10 into e to the power of x. For y100, a to the power of 100 into e to the power of ax. This is as simple as such. Understanding? Yes. So by observing this problem, one important thing I want to tell you is whenever there is some pattern coming like this, then only we can take the nth derivative like this. So whatever the function, first we should check that whether it is in a given sequence or a series. So if it is in a sequence form, then only we can take the nth derivative of that. If not, we should arrange that. For example, let me take some numbers like 1, 4, 9, 60 and etc. There is no some sequence, right? So 1, 4, 9, 16. But you have to convert in the form of sequence, that is first, second, third, fourth. You can do it, right? 1 is nothing but 1 square, 4 is nothing but 2 square, 9 is nothing but 3 square, 60 is nothing but 4 square. Now after this, you can generalize it. Isn't it? Understanding? I hope you people are understanding and it is very interesting. Yes. So this is the function. This is the first standard form. Let me write here. Let me write here. So for the function y is equal to e to the power of ax, yn is nothing but a to the power of n into e to the power of ax. This is the first standard form I am writing. Let us see the second standard form, that is y is equal to a to the power of mx. That is y is equal to a to the power of mx. This is the second standard form we have in the engineering book. So anyway, I am discussing the paper 1 M1 of engineering mathematics VTU syllabus. Okay, so y is equal to a to the power of mx we have. Okay, so how you will be writing it? How will you differentiating? Let me take the first derivative. So y1 is nothing but, so before differentiating it, so what is the derivative of d by dx of a to the power of x? What is the derivative of a to the power of x? So it is a to the power of x into log a, isn't it? So d by dx of a to the power of x is nothing but a to the power of x into log a. Similarly, and you have to write here derivative of d by dx of x, this power. So this is going to become a to the power of x into log a into 1. So that is a to the power of x into log a. Okay, this power what we have a to the power of x, that again we are going to differentiate it. That is the formula we have, derivative of a to the power of x. So here a to the power of x, the derivative of a to the power of x is nothing but a to the power of x into log a. So similarly we will be taking the same pattern here and we'll see how we are going to differentiate this. So a to the power of x is a to the power of x into log a. So similarly I will be taking it a to the power of mx, a to the power of mx into log a into the derivative of this power mx. So here I have taken the power x and x is the derivative of x is 1. Obviously we will be getting the same a to the power of x into log a. So here y1 is equal to a to the power of mx into log a into, again I am differentiating this. See what is going to happen, that is nothing but a to the power of mx into log a, and what is the derivative of mx? We will be getting it as m, right? So can I write it m here? Yes, this is the first derivative. Let us see the second derivative, what is going to happen. The second derivative, I am again going to differentiate this. So we have m already constant, again I am differentiating this. So even log a is constant, right? Yes, even log a is constant here. See how I am taking out, I am going to take it as m log a as a constant and I am going to differentiate a to the power of mx. We know what is the differentiation of a to the power of mx. We have this, right? What is this? The same thing, we'll be getting it. M a to the power of mx into log a. So m log a I am taking it because I am again differentiating this y1 to get the second derivative. So m log a I have taken as constant because it is constant and I am going to differentiate again a to the power of mx. We know already what we have differentiated, a to the power of mx will be getting m a to the power of mx into log a. Understanding? Yes. So here m log a into m a to the power of mx into log a. Again I am going to take, okay, this, what happens, this m log a already it is there. Again I am going to take this m log a and a to the power of mx left. So this is going to become m log a square into a to the power of mx. Okay, I hope you people are understanding. Yes, so this is the second derivative. Okay, again I am going to differentiate this with respect to x again for the third time. This is the third derivative. So already we have a constant m log a the whole square into, now I am going to differentiate this a to the power of mx. Again I will be getting, what I will be getting, m a to the power of mx into log a. Now this can be written because here I have m and here I have a log a. So again this becomes m log a the whole cube into a to the power of mx. So now there is a pattern here. Observe the pattern. What is the pattern here? So in first derivative, a to the power of mx, m into a to the power of mx into log a, m log a to the power of mx. I can write this like this, right? M log a into a to the power of mx. Okay. So y2, m log a square into a to the power of mx. y3, m log a cube into a to the power of mx. y4, m log a, if you differentiate this again, you will be getting m log a to the power of 4 into a to the power of mx. If you differentiate again with respect to 5 successive differentiations, you will be getting m log a to the power of 6 into a to the power of mx. So what is the general nth derivative of this function, that is y is equal to amx? So we can write it as yn is nothing but, okay, so we can take it as dn also. What is dn here? dn is nothing but, so dn by dx to the power of n, which means nth derivative we are speaking about. Instead of writing this, we can write dn also. So dn of a to the power of mx is nothing but, so just replacing this, the increment number, that is m log a is increasing, that here we add power 1, okay, and 2, 3 and goes on. So we can take it in general as m log a to the power of n a to the power of mx, or you can write it like this also, m to the power of n into log a to the power of n into a to the power of mx. So anything you can take. So this is the general form, we have for this type of function, this standard function. So let me write down, so it will be very helpful for us to calculate it. So let me write down here. So what is the second one? If y is equal to a to the power of mx, we have yn is nothing but m log a to the power of n into a to the power of mx. So this is the second standard form. First standard form, we saw it as y is equal to e to the power of ax, then the nth derivative is a to the power of n into e to the power of ax. When y is equal to mx, a to the power of mx, then the nth derivative, we saw how we are going to find the nth derivative. So that is yn is equal to m log a to the power of n into a to the power of mx. Let us see the third standard form, that is y is equal to ax plus b. Function we are going to see, that is y is equal to ax plus b to the power of m. This is the function we are going to see, the next function. Yes, this is the form of the function. So let us see what is the nth derivatives. As we know, the past two formulas we have derived, right? Let me go for the first function, that is y, first derivative y1. How I am going to write y1? It is, you know, derivative of d by dx of x to the power of n is nothing but nx to the power of n minus 1, right? So similarly here we will be getting m into ax plus b into m minus 1 into a, isn't it? So chain rule, you would have been seen in your POC, the chain rule, right? How to differentiate a function using a chain rule. First, targeting the exponent, we have targeted m into ax plus b minus 1 into, for the differentiation of ax plus b is a. Understanding? Yes. So again I am going for the second derivative, that, so m and a are constants coming out, right? I'll be having a here. Let it be there. So m into, again I'm going to differentiate this. What's going to happen? Ax m into m minus 1, I'll be getting, right? M minus 1 into ax plus b to the power of m minus 1 minus 1, that's going to become minus 2 into, already there was a, another a will be getting, then this becomes a square. I hope you people are understanding. Again I am going to the third derivative, that is m into m minus 1, already we have. Now I am going to differentiate this. This is going to become m minus 2 into ax plus b to the power of m minus 3 to a cube, because already we have a square. Again differentiating this, ax plus b will be getting a. So by observing this pattern, what we have observed, so here m is increasing and also here we have a square power increasing, a to the power of 1, a to the power of 2. Then how we are going to generalize this? That is yn is equal to m into m minus 1 into m minus 2 and so on to m minus n minus 1. Observe carefully. So whenever we are taking the nth, any derivative like third derivative, here it is going to end the m minus 1, m minus 1, m minus 2, it is going to end at m minus 2, right? So if you see here, it is 3, it is 2, it is 2, it is 1, it is 1, and there is no only m we have. So obviously we can take like this, m minus 1, m minus 1, so on to m minus of n minus 1, you will be getting it. Isn't it? N minus 1 is happening here. N minus 1, 3 minus 1 is nothing but 2. N minus 1, 2 minus 1 is nothing but 1. So we'll be getting like that. Okay. So now this one we are going to generalize it. So now one thing we generalize, that is with respect to m, we have here, that is ax plus b to the power of m minus n, because it is taking the nth value, right? So whatever the successive differentiation you are doing, m minus 1 into a to the power of n, because a is also increasing. So this is the generalized nth derivative of the function of the form y is equal to ax plus b to the power of m. Yes, I hope you are understanding this. So this is the generalized form. We can write it here. Just we can write it here. So y is equal to, of the form ax plus b to the power of m. So what will be yn? Then yn will be m into m minus 1 and so on to m minus n minus 1 into ax plus b to the power of m minus n into a to the power of n. Okay, so this is the formula we have. Yes, the nth derivative of the function of the form ax plus b to the power of m. Let us see the next function, the next standard function, what we'll be getting. Yes, next standard function where y is equal to 1 by ax plus b. So 1 by ax plus b, we can take this as, we can write this 1 by ax plus b as ax plus b to the power of minus 1. Understanding? Yes. Now we'll take the first derivative. What's going to happen with respect to first derivative? y1 is nothing but, so we'll apply the derivative x to the power of n is equal to nx to the power of n minus 1. So we'll apply it. It's going to become minus 1 into ax plus b to the power of minus 2. Minus 1 minus 2 plus minus 2 into a. Because again chain rule, be careful, you have to write a. Most of the students, they do this mistake while doing, without the general formula also, while doing the successive differentiation, they leave this a, they forget to differentiate this, the inner function. So generally you should remember the chain rule. We are going to first target the power, inner power, inner power, inner function, finally up to x. So this function also we need to differentiate while doing chain rule. So I first handled the exponent, then coming back I am going to differentiate this, will be getting a here. So you should be very careful while doing this. Yes. Next I will go for the second derivative, that's nothing but minus 1 into minus 2 into ax plus b. I am going to differentiate this, I am going to minus 3 into a square. I hope you are understanding. you will be getting ax plus b minus 1. Already we have constant, a already constant. I am going to differentiate this, that is ax plus b to the power of minus 2. I will be getting minus 2 ax plus b minus 2 minus 1 minus 3 into a square. And this one I can write it as, say, observe carefully, minus 1 to the power of 2 into 2 factorial into ax plus b the whole minus 3 into a square. Can I write like this? Even this also I can write in the form minus 1 to the power of 1 factorial into ax plus b to the power of minus 2 into a. What is the meaning of factorial? If you take for example 5 factorial, we will be doing 5 into 4 into 3 into 2 into 1. Similarly 2 factorial, it is 2 into 1. Like this we are going to calculate the factorial, right? Yes. So here if you observe carefully what happens, so minus 1 to the power of 1 is nothing but minus 1 into 1 factorial is 1. So minus 1 you will be getting, no value is going to change. For generalizing this, in order to find the nth derivative of this type of function, we are going to do this. So here also I have put minus 1 to the power of 2, which means minus 1 into minus 1 becomes plus 1. 2 factorial is 2. We will be getting 2. Obviously 2 minus into minus is plus, 2 ones are 2. Yes, and of course the power is increasing here. Similarly, we will go for the third derivative y3, that is nothing but minus 1 into minus 2 into minus 3 to the power of ax plus b to the power of minus 4 into a cube. This is going to become a cube because already we have a square. Again I am differentiating this, ax plus b, I will be getting another a, that becomes a cube. Again we can write this in the form of minus 1 to the power of 3 factorial into ax plus b to the power of minus 4 a cube. Understanding? See, observe the pattern here, similarity, what is happening. By seeing this, how can we generalize? Putting yn is equal to dn. What is dn? dn is nothing but dn by dx to the power of n. So instead of writing this, we will directly write the capital dn, where d is nothing but d by dx. Okay, so d to the power of n of 1 by ax plus b is nothing but, now let us generalize this. Minus 1, 1, 2, 3, it's going repeating. If you take the fourth derivative also, you will be getting minus 1 to the power of 4. So minus 1 to the power of n, and even here 1, 2, 3, it is repeating, right? So I am going to take it as n factorial into ax plus b. So here it is minus 2, minus 3, minus 4, it is happening like this. What's happening? Minus n plus 1, right? It is minus n plus 1. If you take 3, see this is n, right? 1 plus 1, 2, it is minus 2, it is 2, 2 plus 1, 3, it is minus 3. It happens minus n plus 1. We can write this, and also a to the power of n, because a also the power is increasing 1, 2, 3. Now I have written the general form, the overall general form. Writing this in the simplest form, we can write minus 1 to the power of n into n factorial into a to the power of n by ax plus b to the power of n plus 1. So this is the yn, that is the nth derivative of the function of the form 1 by ax plus b. So this is the overall nth derivative, that is yn is equal to minus 1 to the power of n into n factorial into a to the power of n by ax plus b into ax plus b to the power of n plus 1. This minus n plus 1, if it comes down, this is going to become plus n plus 1. So this is the nth formula, nth derivative of the function of this form. I hope you are understanding and enjoying. Okay, shall we go for the next function, next standard function? Yes, so before that let me write it here. That is, if y is equal to 1 by ax plus b, then yn will be minus 1 to the power of n into n factorial into a to the power of n by ax plus b to the power of n plus 1. Okay, so this is the nth derivative. How? Okay, the next function we are going to take, that is y is equal to log of ax plus b. Okay, we know the first derivative y1 is equal to, what is going to happen? We are going to get 1 by ax plus b, that is nothing but ax plus b to the power of minus 1. This is the first derivative, because the derivative of log x is 1 by x. We will be getting the second derivative y2 is nothing but we have minus 1 into ax plus b into minus 2. So here, remember, again you need to differentiate for this, right? You will be getting a here. Sorry, you should not forget that. Chain rule, you should be very careful. Ax plus b to the power of minus 1. We have differentiated. Again, for this function, you are going to differentiate, you will be getting a. Okay, so again, minus 1, this constant, I am going to differentiate this. Constant is as it is, we have a, and I am differentiated. Again, another a will be getting, I will be getting a square here. Okay, so again, the third one, the third derivative, what is going to happen? We will be getting minus 1 into minus 2 into ax plus b to the power of minus 3 into a cube, because again when we differentiate this, we will be getting another a. Okay, understanding? Yes. So next, if it goes on like this, the pattern continues. Okay, so here the pattern continues, a to the power of 1, a to the power of 2, a to the power of 3, and it goes on like this, isn't it? Yes. So how will you write? So here I can find the pattern minus 1, minus 2, all these things. But how can I write this? So this can be written as minus 1 to the power of 1 into 1 factorial into ax plus b to the power of minus 2 into a square. Isn't it? So this can be written as minus 1 the square into 2 factorial into ax plus b to the power of minus 3 into a cube. So what's happening here? See, factorial minus 1 to the power 2 is minus plus 1, right? It is even. For even, the negative sign will be plus. For odd, the negative sign will be the negative itself, minus. So here we will be getting minus 1, obviously we will be getting minus 1. There is no change. Just for our convenience, to make it as a generalized form, generalized nth derivative of this function of the form log of ax plus b, we are doing this. Here also, we are doing the same. And also here also you can do the same, that is, you can write this as minus 1 to the power of 0 into 0 factorial into ax plus b to the power of minus 1 into a to the power of 1. Okay, so minus 1 to the power of 0 is 1. 0 factorial is 1, obviously. So here if you take, so you can make this as the same value, it doesn't change. So we have, for our convenience, we have taken this. So what will be writing for the nth term, nth derivative? So yn is equal to dn of log of ax plus b. We will be writing it as minus 1 to the power of n, because the power is increasing, right? Sorry, if you have first derivative, you have 0, right? So you are going to put n minus 1. Right. For the second derivative, you have 1 here. For third derivative, we have 2 here. So it is n minus 1, right? So minus 1 to the power of n minus 1 into, this is n minus 1 the factorial. Because if it is third derivative, you have 2 factorial. If it is second derivative, 1 factorial. If it is one derivative, first derivative, 0 factorial. So this is n minus 1 the factorial. We can write like this. And ax plus b, the whole power, minus n. With third derivative, we have 3, but with the minus sign, minus n. I am writing in terms of the generalized form for finding the nth derivative of that function, and a to the power of n, because 3 and 3, 2 and 2, 1 and 1. So obviously there you will not be getting n minus 1, you will be getting n. So writing this in the simplest form, so yn is nothing but minus 1 to the power of n minus 1 into minus n minus 1 the factorial into a to the power of n by ax plus b to the power of n. So this is the generalized nth derivative of the form of the function of the form log of ax plus b. If you want to find the nth derivative of this function, so then you will be having the yn is equal to minus 1 to the power of n minus 1 into n minus 1 the factorial a to the power of n by ax plus b to the power of n. This is the generalized form of the nth derivative of the function log of ax plus b. Next, we'll go to the next generalized form. So before that, okay, so we can write this. We have yn is equal to log of ax plus b. So y is equal to log of ax plus b, then yn will be minus 1 to the power of n minus 1 into n minus 1 the whole factorial into a to the power of n by ax plus b to the power of n. Okay, so this is the formula we have, the nth derivative. Okay, so next we'll go with the standard form of trigonometry, that is y is equal to sine of ax plus b. We have the function, it is sine of ax plus b. So now the first derivative y1 is equal to, we have cos of ax plus b into a, isn't it? So because the differentiation, the derivative of sin x is cos x, and we are going to differentiate this, we'll be getting a. Okay, so when we take the second derivative, what is going to happen? It's going to be minus sine of ax plus b into a square. Cos sine cos, it will go alternatively, so we will not be getting a pattern. So what I am going to do, dealing with the trigonometric functions is very beautiful, and some substitution whenever in calculus or any part of mathematics, when some trigonometric functions come, then obviously the formulas of trigonometry and the angles, theta, all these things comes into picture. So here I can take like this, that is cos theta can be written as sine of pi by 2 plus theta. Can I write like this? Sine of 90 plus theta is cos theta, isn't it? So cos theta I'll be writing in this form, that is sine of 90 plus theta. So the same thing I can write it as y1, the first derivative is a into sine of pi by 2 plus ax plus b. Understanding? Just I have written the cos theta is equal to sine of 90 plus theta. So next, second derivative I am going to do. A already we have, another a will be getting when we differentiate this. So I will write that. So again for sine it is going to become cos of pi by 2 plus ax plus b, right? So now again I am going to change. What happens? For cos of pi by 2 plus ax plus b, we will be getting a square into sine plus pi by 2 plus ax plus b, right? So I have differentiated, I will be getting this. So what we have, a square into sine of, we have 2 pi by 2 plus ax plus b. Okay, so this is the second derivative. Next we will go for third derivative. We will be getting a cube, because here we will be getting a. So a cube into, for sine we will be writing cos of 2 pi by 2 plus ax plus b, right? Just differentiating sine. And for this a already I have written it as a cube. So again converting this cos to sine, what happens? Sine of pi by 2 plus 2 pi by 2 plus ax plus b. I hope you are understanding. So this is going to become, so a cube into sine of 3 pi by 2 plus ax plus b. So by observing this pattern, what is happening? Understand carefully. I am substituting in the place of cos theta sine of pi by 2 plus theta. So in the place of cos ax plus b, already we have a sine of 90 plus ax plus b. Analyzed from how you can write this. So yn is nothing but dn of sine x is nothing but a to the power of n into sine of pi by 2 n plus ax plus b. So this is the generalized form we can write for the function sin x, that is a to the power of n into sine of pi by 2 n plus ax plus b. So this is the generalized form of sine of ax plus b. I hope you are understanding. Yes? Yes. We can write it here, that is, if y is equal to sin x, then yn is nothing but we have a to the power of n into sine of n pi by 2 plus ax plus b. Okay, so next function, the standard form y is equal to, which one we are going to take? We have taken sine, let us take cos. Then what happens if we take cos of ax plus b? What is going to happen? So cos of ax plus b. So we have the first derivative, that is equal to minus sine of ax plus b. Okay. So what happens here, if we observe, we have minus sine theta is equal to cos of pi by 2 plus theta. Isn't it? Minus sine theta is nothing but cos of pi by 2 plus theta. The ASTC rule, all the trigonometric things, I hope you know the trigonometric functions, the trigonometric formulas, how it is going to have it. We have this formula, minus sine theta is cos of pi by 2 plus theta. Yes, so here we are going to substitute into a. Here we will be having minus sine into a. So minus sine theta I am going to write in the form of cos of pi by 2 into plus ax plus b into a I will be writing. So minus sine theta I will be getting cos of pi by 2 plus theta, that is 90 plus theta. Okay, so next I am going to differentiate this with respect to x. Again we will be getting y to a, already I will be getting another a, that is for cos it is sine. So it is minus sine of pi by 2 plus ax plus b. Right. So here a square into, for minus sine theta I have cos of pi by 2 plus theta. So cos of pi by 2 plus pi by 2 plus ax plus b. So what happens here? A square into cos of, we have 2 pi by 2, right? So 2 pi by 2 plus ax plus b. I hope you are understanding. So similarly we will be having y3 is equal to a. When you differentiate this you will be getting a here. Already we have a square, we will be getting a cube into, for cos again you will be getting minus sine of 2 pi by 2 plus ax plus b. So that is nothing but we have a cube, okay, minus sine theta cos of 90 plus theta. So we will be getting cos of 3 pi by 2. So here it becomes 3 pi by 2 plus ax plus b. Right. So this is the pattern we have observed. A square, a square, okay, a cube, and goes on like this. So in general, how can you generalize this? Y to the power of n is nothing but a to the power of n cos n into pi by 2 plus ax plus b. So this is the general nth derivative of the function cos of ax plus b. Yes, so these are some of the standard functions I try to discuss today. In the next video, maybe in 2 to 3 days, I will be coming up with some other general forms, general standard forms, and will directly go to problems. This is the concept of successive differentiation. Today we saw what is successive differentiation, and also we saw how to derive a formula, the generalized formula of nth derivative, which is very useful and very important and so beautiful concepts. So take care, be mathematically inclined towards your thought process, and thank you for watching this video. If you like this video, like it, share it, comment, and don't forget to subscribe my channel. We'll have a great journey of mathematics. Bye bye. Take care.